Good morning. Good morning. Hope I am audible. Am I audible? Good morning to all. Am I audible? Okay. So today we are going to learn the separately excited DC motor analogy of induction motor. Basically, I am going very slowly so that it will be convenient for all of you to follow. Okay, but the thing is, please don't miss the classes, because if you miss one class, then the next class you may not be able to follow. Okay, because it's a very big subject and vast subject and popular subject, so that's why I'm giving you the complete glimpse, even though it is not possible within that 10-15 days, but I am trying my level best. Okay, at the end of the class, this course, your maximum question it will be answered, because now say I am teaching you the separately excited DC motor analogy of induction motor. Your mind, you may ask me, why sir, why I should learn this? Definitely it's, your question is valid, but there is I have framed the lectures such a way that it is easier to you to follow the things rather than telling the entire thing together. Okay, so in this lecture I'll be using slightly mathematical calculations. So I have used some suffix. Already we know what is direct axis and quadrature axis. Already we have learned it yesterday from 3-phase to alpha beta, that means ABC to alpha beta, which is stationary reference frame, then alpha beta to DQ. DQ is the rotating reference frame. It is rotating, always making some angle. There will be some instantaneous angle theta with the alpha axis. So DQ reference frame, entire D and Q which are in quadrature, and it is rotating. Okay, so if I use any suffix SD, that means stator direct axis, RD rotor direct axis, SQ stator quadrature axis, RQ rotor quadrature axis. Okay, so now the standard voltage equation, already who are electrical engineer, they already learned the mathematical modeling of rotating electrical machines. So definitely they are familiar with this. Even though if you are not familiar also, you can write it. So this is stator direct axis voltage. So voltage basically it's a product of, if you apply Kirchhoff's voltage law, so this is the drop across the resistance. So the current flowing through it is through the circuit is ISD. So RS, this is the stator resistance into stator direct axis current, and rate of change of flux with respect to time, that is also voltage, and minus, which is opposed by the quadrature axis flux, that is due to the rotation. This is also basically omega is equal to d theta by dt. Okay, so here also voltage will develop. So from this equation, because now we are going to find out the electromagnetic torque produced by the machine. So torque means, you understand from the name itself, we need to find out the rotational power. So to find out the rotational power, you need to find out the rotational voltage. So stator direct axis rotational voltage is this part only. So I have segregated it. So this is the rotational power from the stator direct axis, rotational voltage. This is the rotational voltage from the stator direct axis. Similarly, for quadrature axis voltage equation, if you write, it is like this, but it is not opposing, it is adding. If you say the phasor, you will be understanding it, but I am not going to all these details, and I am assuming you know, everyone know the mathematical modeling, high performance dynamic modeling of machine, and the phasor diagram of the motor. So from here, this is the rotational voltage. So I have written this. Okay. Now the total rotational power is voltage into current. So that's why I have written this is VSD rotational into ISD plus VSQ rotational into ISQ. It's very clear, this slide. Okay. So now I am replacing this psi SQ. This is the flux. So this I have written. So flux is basically product of inductance and current. So here I have used one term LSS. So this is basically self plus mutual. Stator self inductance plus the mutual inductance, which is coming from the rotor side. So psi SD is equal to LSS ISD plus LM IRD, because it is coming from the rotor side. Similarly, psi SQ is equal to LSS ISQ and LM IRQ. This is mutual part coming from the rotor side, R, rotor quadrature axis. Now in here, in psi SQ and psi SD, if I replace by this and this, and I will simplify, then the equation is converted like this. Omega S. So omega S, you know, this is the synchronous speed. Already you know. So omega S Lm into IRD ISQ minus IRQ ISD. But as I was telling, rotor is rotating. So always we need to substitute the rotor currents or rotor electrical parameters, because we don't have any method of direct measurement. Okay, we need to substitute it. So now similarly, the rotor direct axis flux is nothing but LRR. Again, this LRR means rotor self inductance plus the mutual inductance, which is coming from the stator side. So that's why I have written LRR IRD plus LM ISD. So as I told, these things I have to replace. So if I find out the IRD, so it is like this. Similarly, psi RQ is equal to LRR IRQ plus LM ISQ. So I have to replace this IRQ. So IRQ is nothing but this. Okay. Now in that equation, here you see, this is the value of IRD and this is the value of IRQ. So now if I replace it and simplify it, then the equation is converted like this. Total rotational power consumed by the stator is Lm omega s by LRR into psi RD into ISQ minus psi RQ ISD. Okay, very simple mathematics. Now the rotational power, let us, why we know, we should know the basic. Say this is a circle, a radius r and a particle is rotating like this, and if this is the theta which is in radian, after t second from this is the initial position, it is going this position and traveling the arc s. So my s is equal to r into theta. Now if I divide it by both sides by t, so this is my linear velocity into angular velocity. It's meter per second, it is radian per second. Now the work done is force into distance. Now the power is work done by unit time. So force into s by t, which is nothing but force into velocity. So velocity, we already obtained this, so into r into omega. What is this F into r? So force is applied like this. This is the F and r. So this creating one couple. This is basically torque. So basically your power is nothing but the product of torque and angular speed. But power, this is basically coming from the rotor shaft. So that's why I have used mechanical. Okay, omega s mechanical, omega s rotor side. But as we know, keep from the stator side, if I want to go to the rotor side, already we learned that RPM synchronous speed calculation. When you are going to rotor side, you have to divide that stator frequency by pole by 2. So omega s mechanical is nothing but the omega s stator divided by pole by 2. So that's why I have written torque into omega s by pole by 2. which is nothing. This already we calculated this value already we calculated. So now torque is equal to this omega s cancelled out. Okay, so my torque is equal to P by 2 by omega s. This omega s cancel, and Lm by Lrr into psi rd isq minus psi rq isd. Okay, so it is finally coming like this. Now you remember we converted the 3-phase power to 2-phase power. Once we have converted this ABC to alpha beta, the 3-phase converted to 2-phase. So definitely to balance the power, I have to multiply the entire thing by 3 by 2. So that's why I multiplied this final things by 3 by 2. Now this pole for a machine is constant. The inductance, mutual and the total inductance of rotor also constant. So this entire term 3 by 2 P by 2 Lm by Lrr, this is also a constant. Okay, so you remember the instantaneous torque equation of induction machine, any induction machine. Okay, it is given by 3 by 2 in case of for a 3-phase machine, 3 by 2 into pole by 2 into Lm by Lrr into psi rd isq minus psi rq isd. This is the standard equation. Now I think there is no difficulty to understand how it has come. Now coming to the torque equation of separately excited DC machine. If you remember our first lecture, I have told the combustion engines cannot operate with constant torque for all the RPM. That's why this gear mechanism is introduced to adjust the mechanical advantage required time to time. Okay, when I need higher torque, I have to bring down the wheel RPM. So we'll apply clutch and change the gear, and vice versa, and so on. But in electrical machine, for the entire operating range, you can apply the maximum torque for all the RPM. How it is? That concept came from the separately excited DC machine. You see the torque equation here, it is basically equal to some constant into flux into armature current. Here omega is not present. But for combustion engine, this torque is dependent on omega. But in separately excited DC machine, torque is independent of RPM. This is called decoupled control. Without touching the torque, I can change the RPM. Okay. But for induction machine, squirrel cage induction machine, this analogy is directly not possible. You see, there two components are there. If you remember the torque equation which we have established, that is psi rd into isq minus psi rq isd. There is a vector summation of two flux, and another is opposing, negative. So it is coupled. The torque equation is coupled with the two flux, but I have to decouple. And another interesting thing for back EMF, for separately excited DC machine, that this is the back EMF. That back EMF is independent of armature current. And if you see the construction of separately excited DC machine, the armature flux and the field flux, they are quadrature. So cos 90 is 0. So the field flux is not influenced by armature flux, and the armature flux is not influenced by field flux. This is the unique thing. That's why I was telling that till late 70s, even though today, so many places where the speed control is concerned, except few cases where hazardous operation is not permissible, all those places people using separately excited DC machine with old technique, that Ward Leonard and this kind of technique, because that is very easy. Even though there are difficulties, it is not economic, periodic maintenance are required, but still people are using it. Is easy. Now you see, for induction machine, if I want to control in a decoupled way, which is decoupled means same as separately excited DC machine, how it is controlled. If I want to do that same thing for induction machine, I have to convert the torque equation of induction machine to this. Okay, very clear. So already we know the torque equation of separately excited DC machine is some constant into field flux into armature current. Okay, so now this is the torque equation for an induction machine. Now this is to be converted like this, then only I can operate an induction machine analogous to a separately excited DC machine. As I told, these all are the passive parameter for induction machine. We can take it as constant. Now if I make this term as 0, psi RQ as 0, okay, if I make this psi RQ as 0, then this term will be vanished, and my torque equation, it will be converted as K into psi RD into ISQ. This is so this is constant, and this psi RD I can equate it to my field flux, and the ISQ I can equate it to armature current. Now from the discussion we have done so far, what we understood: to operate an induction machine for a decoupled control, that means if I want to control the torque and the RPM in an isolated manner, I have to operate an induction machine analogous to a separately excited DC machine. To do so, what is the mathematical inference? Mathematical inference is the torque equation of an induction machine is to be equated with the torque equation of separately excited DC machine. So to do so, this quadrature axis component of the rotor flux is to be equated 0. If I am able to do that by adopting some control technique, then my target is achieved. I will be able to operate the induction machine analogous to a separately excited DC machine. So now you see, if this is my direct axis and if this is my quadrature axis, my rotor flux is somewhere here. So this is my direct axis component and this is my quadrature axis component, and entire that dq is rotating with the synchronous speed. Now how to make this psi rq 0? You make theta 0. If you make theta 0, then this psi r will be aligned with direct axis, and my quadrature axis component, it is like this. Psi is, if you see in this here, psi rq is this much only. Now again, if I align perfectly, my psi rq will become 0. Actually, vector control or field oriented control is nothing to, for all machines, BLDC, synchronous machine also, everything is nothing to make this psi rq 0 by some method. So now if I tell technically, what do you mean by field oriented control or vector control? So the first thing is, I have to make the separately excited DC machine analogy which is applicable to induction machine. To do so, I have to equate the instantaneous torque of induction machine, which is identical to the torque equation of separately excited DC machine. To do so, I have to make psi rq 0. To make psi rq 0, I have to align the rotor flux with direct axis. This is called vector control. So I will tell these things in a single line. Vector control of electrical machine is nothing but to align the instantaneous rotor flux with the direct axis of synchronous rotating reference frame. I repeat once again. Vector control or field oriented control is nothing to align instantaneous rotor flux with the direct axis of synchronous rotating reference frame. Okay, so hope it is clear to you. I am able to clear you what is the separately excited DC motor analogy of induction motor. Now here so today I will be showing you one more thing. Yesterday for ADC, if you remember, I have given a pause to the controller, that means the program counter or the stack pointer. I kept in a loop, infinite loop, till the conversion is completed. So till the conversion is completed, microcontroller will be not doing any other job. which is not a good practice. If you alone use a card for only ADC, then it is okay. But if you use one controller for several other purpose, it will generate PWM, you are using timer, interrupt, so many things, then it is not correct. You should not put a pause to the controller. For that, a very good things are there in microcontroller, which is called interrupt. Let me explain you what is interrupt. Say I am taking class to you. Okay, I am explaining the ADC. Now suddenly my HOD came in my home. Then what I will tell? I'll tell, please excuse me, my HOD has come. I have to speak with him. Then I will go to him, I will attend him, I will talk to him. Once it is finished, then I will come to you again, and where I stopped, from there I will start to teach you again. So to enter of my HOD in my room is called an interrupt. Okay. Now do you take one more example. I am teaching you ADC. Suddenly my HOD entered in my room. I have to go to attend him. While I was attending him, immediately my director entered in my home. Then I will tell my HOD, sir, please you wait. I have to attend my director. I will go and I will talk to him. Once it is finished, then I will come to my HOD. From where I stopped, I will start to discuss again. I will finish, and again I will come to you and start to teach from where I resume, from where I left. This is called the priority of interrupt. If so many interrupts occur together, which interrupt to be addressed, that is predefined for microcontroller. We have to understand that also. When I am using overflow interrupt to generate PWM, which interrupt I have to take first? All these things. When ADC interrupt and all other external hardware interrupt is occurring together, then which interrupt will work first? Based on that I have to write my code. This is not this for any controller. We have to know that. And always you remember, you should not put any delay in any code. This I learned from my professor. He told always try to avoid that. You may not be understanding the consequences. Something may happen. Don't do that. Okay. So here similarly in this code, you see, this is ADC underscore init. I am initializing. Here I have used one additional register and the 7th bit I made enable. So let us see what is that. You see, this is the SREG. 7th bit is the global interrupt enable. If I want to use any interrupt, I have to first enable the I bit of the status register. So that is the 7th bit. So that's why I used. And here I have used one more bit of ADC SRA, that is ADIE, which I have not used yesterday. So let us see what is ADIE. This is my ADI, that is the third bit. So when this bit return to 1 and I bit of the SREG is set, already I have set, the ADC conversion completed interrupt is activated. I need not to put any pause. Once ADC conversion is completed, it will generate one interrupt. Okay, it will generate one interrupt. It's very good. I need not to bother. I need not to put the hold. Once conversion is completed, automatically it will go to, it will create that interrupt. So for that I have used this bit. Remaining things are same as earlier. Now here I have writing one service routine. ISR means interrupt service routine, and this is the vector for ADC interrupt. Here I am defining one variable where the ADC word it will be stored, and I am using the switch case statement. You know, all you know switch case, because you know C, hope you are doing all Python, Java, all these things, so you very well know what is switch case. In ADMARCs, the first 4 LSB, it is set 0, 1, 0, 0. Why it is so? Because those are the reference bit for the analog reference voltage selection that already I have discussed yesterday. Now the first thing is the first channel. I am using channel 1 and channel 5. So first it will go to channel, it will take the analog value from the channel 1. Once that conversion is over, then I am changing the ADMARCs value to 5, fifth channel. Then immediately it will break and it will go to this case. And once this conversion is completed, I am changing the ADMARCs value to 1, 4, 1. 0x means hex. That means again it is going to first channel. So first, then fifth, fifth, then first. Like that if you want to do for all, so first, then second, then third, then fourth, then fifth, then 1. It is going on, going on, going on. So what is the advantage of this thing? I am not putting any hold. Microcontroller is it's keep on doing its work, and once the interrupt occurring, once the conversion is occurring, it is taking the value and using in the calculation. It is not holding anywhere. So this is the advantage of the interrupt. So let us see the simulation. Already I have loaded this. You see, it is changing channel 1, channel 5. So you have, hope you have understood the application of interrupt why ADC interrupt is used. Because this, wherever what required one by every time I will be, rather than telling all these things together, I will be telling you sequential. So this is all about today's lecture. Now you can ask very low, but I am seeing in the recording it is quite loud. Now you can, सर संडे क्लास का टाइम का मुझे मैसेज नहीं मिला. एक्चुअली मैं तो मैसेज नहीं करता हूँ, तो सबको पता चला आपको क्यों नहीं पता चला, मेरे को समझ में नहीं आया. Okay, now this is all about today's class. Now you can, now some 4-5 minutes are there. You can ask question. If you have any question, you can ask. If you don't ask any question, there are only two options. Either you understood completely, or you completely can't understand. There's two thing only. If you don't ask any question, that means you understand completely, and if you, or you won't understand anything. These are the two options. Any question is there? Somebody at least reply no question or something like that, then I can terminate. Yeah, that FOC will be applicable to BLDC. I'll be showing it. I'll be showing it. Okay, thank you so much. So thanks a lot. We will see tomorrow.